In this section, you will study general optimization problems formulated with both inequality and equality constraints. The given problem is the primal problem. We'll first introduce its dual formulation and then try to figure out certain relationship between the primal problem and the dual problem. Let's get started with this general optimization problem. We want to minimize f of x. Now, subject to satisfying these conditions, part of conditions is along with inequality, the other part is with equality. Now, we define as a Lagrangian. We call this function Lagrangian. That is, now f of x, the original objective function, and after multiplying alpha I, we have a sum here, and multiply here beta j and sum. That is Lagrangian. In vector notation, we can write in this way. And for this portion is alpha dot h, and for this portion beta dot q, and alpha, so that alpha is a vector of length m, and beta is a vector of length p. And these are called the Lagrange multipliers. Okay, this is the Lagrangian. Now we define the feasible set C, and feasible set C is collection of x such that the constraints are satisfied. So when you try to minimize f of x, x must be chosen from the set. Once x is out of this set, then some of these conditions are not satisfied, so that your minimization is wrong. Okay, so you have to find x inside this feasible set. Okay, so we define the set because we use set, and later on, look at this lemma. For each point x in the feasible set, which means that these two conditions are satisfied, assume we choose x, then now f of x is the same as, and for this Lagrangian, we try to maximize over the multipliers, then and that's the same. And this one is happening when alpha I, hi, the product is 0 for every I. Okay, let's see here. Once you choose x inside a feasible set, then we have h is non-positive. Q value is 0. So that the Lagrangian, okay, this portion in alpha is non-negative, so that this whole thing is non-positive, and this will be 0, so that f is larger than or equal to this whole thing. And once you try to maximize, which means that, anyway, here, this is a non-positive, so maximum value of this one will be 0. And also, of course, this one, and because q is 0, this is 0. So that now here, this equality happens. So maximum of the Lagrange multiplier must be f of x. So we know that. Now, clearly, equality happens when these are completely zero, which means that alpha I, hi is zero. And multiplication is zero means that one can be non-zero, and then the other one must be zero. If alpha I is zero, then hi may not be zero. But if it is non-zero, then hi must be zero. So that zero, non-zero. Zero is tight, and non-zero is not on the boundary, so it's loose, it's slack. So its complementary slackness is made, the name is made because of this one. And we'll see the details of complementary slackness later on. So here the main, the result is now maximum of Lagrangian is the same as original objective function, and at the moment this complementary slackness must be satisfied. Now for this Lagrangian, and we defined the feasible set, once x is not in the feasible set, so at least one of them is broken, is not satisfied, then maximum of this one will go to infinity. For example, one of these functions is now positive, then by choosing the corresponding alpha very large, we can make it infinity. And also, if it is a non-zero, and at least one is a non-zero, then we try to choose beta, and so that the product is positive, and try to choose the very large beta so that we can make infinity. So once x is not in the feasible set, then the maximum of the Lagrangian goes to infinity. Now, f star is optimal value of the primal problem, which is minimization over the feasible set of f of x. F star, we use this notation. Then f star satisfies this one. So that now here, and okay, now for that one, we already know that for this portion, we already know earlier, once x is inside the feasible set, then that is the same, okay, inside, that is the same as f of x. That is same as f of x, so that minimum is the same as this one. But once it is not in the feasible set, then it will go to infinity. So among them, this minimum part will choose the value. So that eventually, now here, f star is now can be written in this way. So this is original f star from definition. Now it can be obtained through this problem. But here x can be arbitrary. Once it is inside the feasible set, then it's the same as, this portion is the same as f of x, so that we reach at this one. Once x is outside of the feasible set, then it will go to infinity, so we discard it. So eventually, these two problems are the same. Here, x doesn't have to be in the feasible set. X can be chosen arbitrarily, but this problem will make the same result, the desired result. So that means that this problem is the same as original problem. Okay, so here we summarize what we have done. The primal problem is equivalent to the minimax problem. Min-max. You can say min-max problem or mini-max problem. So this problem and original minimization problem, along with here the original function f, two problems are the same. So that when we try to solve the original problem, and we may try to solve this problem, this minimax problem. Of course, here Lagrangian is defined in this way, and also here x doesn't have to be in the feasible set. So automatically, this minimum part will choose the desirable solution. Okay, that's the summary. Now we'll go to dual formulation. Okay, start with this dual function. We define g of alpha beta, that is minimum of the Lagrangian. So now is minimization over x, and we try to apply this minimization over the Lagrangian. Then with this definition, we can say that this dual function is always a lower bound of the primal optimum. Okay. Now alpha is non-negative. Then for C in the feasible set, we can say that one, because if you look at the Lagrangian, then alpha is non-negative, and then H is non-positive, so that this portion is non-positive. And of course, this one, once feasible set is considered, then that will be 0. So that now f is, because that one is minimized, so that f will be, okay, for every Lagrangian, anyway, fx is always satisfying this one. And then you are taking minimum over x, so that again, possibly it becomes smaller. And that is, by definition, g of alpha beta. So that we have this low bound property. This dual function is always below of the primal solution. Okay. Now, here we define the dual problem. And so far, we considered minimum part. And now we apply here maximum over alpha beta, and subject to alpha is non-negative. So we formulate this problem, and we call it the dual problem, and which is max-min problem. Okay, now this max-min problem is simply obtained eventually from this original primal problem by changing the order. Rather than min, max, we are considering now max and min. Just change the order. Then that is the dual problem. Okay? And it's quite clear to see from the definition then optimal value. So once you try to find an optimal value, then minimization of that one is this portion is now g and alpha beta, the dual function, and we try to now maximize and over alpha beta. But earlier, we know that for every possible alpha beta, of course, is non-negative, and this function is always below of the primal optima. So that even though you take maximum over alpha beta, and yet this is below. So we say G star is the optimal value for this maximum problem, but yet it is bounded by f star. Right? Okay. Although the primal problem is not convex, the dual problem is always convex. In fact, it is concave. Here we have a theorem. The dual problem is a convex optimization problem. So it is easy to optimize. Okay, let's look at here. Once you consider minimum part, then that is dual function g of alpha beta. That is in detail this one. Now, for given alpha beta, and we try to make that one the quantity, and through this minimization we'll try to find the minimum. But once we look at these terms as a function of alpha beta, then this is linear function. Here we say this affine function of alpha and beta. So in alpha beta domain, it's a line in a sense. So for each x, it is making a line. And for example, in alpha beta domain, it's a line for an x, and for another x, it can be another line, and for other x, it can be another line, and again another line, and so on. Now, among these lines, we try to choose minimum over x, so that we try to choose minimum. Then that is now, there's the minimum, it's a minimum. Okay, that the red curve is a concave curve. So that's the idea of the theorem. Once you consider the dual problem, then it is concave, so it's much easier to solve. Okay. Now we summarize what we have done given the optimization problem. Now this minimax problem is equivalent to the original problem. So we say this is the primal problem. And of course here Lagrangian is defined like this. And change the order so that we have maximum problem. Then this is the dual problem. Of course, if we try to do this portion, then that is the dual function g of alpha beta. Now, here, the Lagrangian is a lower bound. And even though you do maximize, anyway, always is a lower bound. So that in both sides, okay, both side minimization, so that you can get this inequality. Of course, here maximizing through over alpha and beta, and you can get G star, the optimum of the dual problem. Then, yeah, this is lower bound of the primal optimum. But here the one good news is that this dual problem is a convex optimization problem, which can be solved much more easily. Now, here we'll close the section with how to solve the dual problem. Look at this definition we considered earlier, and Lagrangian is defined in this way. Now, its dual problem is formulated in this way, maximum problem. To solve this problem, dual problem, we first consider this minimum part. Okay, we'll focus on this part. Assume we have optimum point and optimal multipliers, x star, alpha star, beta star. Then for this Lagrangian, and we try to make x derivative, so gradient of Lagrangian with respect to x, and now x alpha beta is replaced by here the optimal point n parameters, then the value must be 0. This equation introduces the so-called KKT conditions, or first derivative testers, because this one is first derivative. Once you try to make the gradient x derivative for this Lagrangian, then you'll see this one now equals 0. By solving this one, you can find now this optimal points. Just try to solve that one. First derivative is 0. And when you try to solve this one, you need conditions. The primal feasibility must be satisfied. H must be always non-positive, Q must be 0, and then now of course dual feasibility, alpha must be non-negative. And also earlier we saw that once optimum happens, then this complementary slangness must be satisfied, so that we have another condition, alpha dot h must be 0. So that is the system of equations to be solved, to decide here alpha, beta, and x. Okay. Now, it can be solved depending on the algorithm, and we can get x, alpha, beta simultaneously, or you can get alpha, beta first and then x. In reality, this inequality is along with the functions and vector functions, and so that in many cases it's not so much convenient. So we may try to introduce slack variables, for example z, so that we can reformulate equivalently in this way. So here, now there is a non-negative, non-positive, so add something, so it is a non-negative term z such that it can be 0. So if z is non-negative, then the same as here h is non-positive. So we can say this one is 0 equal, and q is the same. Now alpha dot h is 0, alpha dot h is 0. So addition is 0, alpha dot h is 0, so that alpha z must be 0. So rather than alpha dot h, we may use alpha z equals 0. And then now we have one more condition. Here z must be non-negative. These are all equalities, and these are now parameters, so that it's not a function anyway. It's parameters, and they are non-negative. That is a requirement. So along with this first equation and along with that conditions, we can solve the problem more conveniently. Okay, that's how we can solve the problem. Okay, this is the end of the section. Thank you.